Hi everyone. Today we are going to look at some convolutional neural network architectures and their applications for image classification. In my opinion, the big breakthrough in deep convolutional neural networks happened with this paper. In 2012, there was a large-scale image classification challenge. This paper introduced a new convolutional neural network architecture for that problem and showed how to train the network efficiently with more than 1 million images using GPUs. They used a subset of the ImageNet dataset for training their neural networks. That time, the ImageNet dataset contained 15 million images in about 22,000 categories. The images were collected from the web, and they used human labelers to label each image. The image classification challenge, called ImageNet Large-Scale Visual Recognition Challenge, used only 1,000 categories and 1.2 million images. That means that roughly in each category there were about 1,000 images. 50,000 images were set aside for validation purposes, and 150,000 test images were used to evaluate the neural networks. The images have red, green, and blue channels, and they were preprocessed to have size 256 times 256. Below, I'm showing some random examples from the ImageNet dataset. As you can see, the quality of these images is quite good, and these images indeed cover a wide range of categories. There were two different kinds of tasks. The first task is to make a guess about the label of the image, and then we calculate how many times we predicted correctly the labels on the test set and how many times we made an error. This is called the top 1 error of our predictions. In the second task, we can make 5 guesses about the class labels. If one of them is correct, then we count it as correct prediction. The error of this on the test set is called the top 5 error. The deep neural network that won the ImageNet challenge in 2012 is called the AlexNet. It won by a very large margin over all the other competitors, and this network used several tricks and novelties that were not common that time. The first novelty is that it used GPUs instead of CPUs for training the neural network. The second novelty is that it introduced the ReLU activation function. Neural networks before AlexNet mostly used sigmoid type activation functions that look like the TAN-H function. The AlexNet instead used the ReLU activation function, which is just simply the max of 0 and x. It has been empirically observed that with the ReLU activation functions, the neural networks trained several times faster than the equivalent neural networks which used the TAN-H activation functions. Here you can see some results supporting this claim. A 4-layer convolutional neural network with ReLU activation functions, that's the solid line, reaches a 25% training error on a dataset 6 times faster than an equivalent neural network with the TAN-H activation functions. That's the dashed line. This figure here shows the structure of AlexNet. The AlexNet takes images as inputs. It assumes that the size of the images is 224 times 224, and the images are colored images with red, green, and blue channels. The first layer is a convolutional layer. It has 96 channels, so we have 96 convolutional kernels. The AlexNet uses 2 GPUs. These convolutional kernels are tensors, and their size is 11 times 11 times 3. Out of these 96 convolutional kernels, 48 are placed on the first GPU and 48 are placed on the second GPU. The stride parameter of this layer was set to 4, And the output feature maps of this convolutional layer has size 55 times 55 with 48 channels on each of the two GPUs. The next layer is a pooling layer. The layer partitions the input tensor into a set of subtensors, each having size 5 times 5 times 48 channels. We set the stride parameter to 2, and this layer downsamples the feature maps and reduces their sizes from 55 times 55 to 27 times 27. Later, other pooling layers will reduce this size further from 27 times 27 to 13 times 13. The pooling layer also increases the number of channels from 48 to 128, and later on deeper level channels we will increase it from 128 to 192. We use max pooling on both of the GPUs. For each submatrix with size 5 times 5 times 48, this max pooling layer outputs this expression here. For each channel I, the trainable parameters are W1I and W2I. These are real numbers. In this first pooling layer, I is going from 1 to 128. And on deeper level pooling layers, it can go from 1 to 192. The first pooling layer is followed by a second pooling layer. As you can also see, these two GPUs are communicating with each other. Generally, we should try to avoid GPU communications with each other as much as possible because communications between GPUs are slow. We have more convolutional and pooling layers in this network, and on the deepest layers, we use 3 fully connected layers. The very last layer outputs a 1000-dimensional vector. Below this output layer, we have two 2048-dimensional feature vectors on each GPU. That's altogether a 4096-dimensional feature vector. To summarize, AlexNet is trained with stochastic gradient descent on two NVIDIA GTX 580 GPUs for about a week. The neural net has 650,000 neurons, 60 million parameters, and 600 million connections. It uses 5 convolutional and pooling layers and 3 fully connected layers. To reduce the risk of overfitting and use more data for training, we extend the data set using label-preserving transformations. In particular, we apply the following forms of data augmentation. We translate the images with a few pixels, we do horizontal reflections, and we change slightly the RGB color channel intensities. Another idea that was used in this paper and proved to be very useful to avoid overfitting is the dropout trick. As far as I know, it's just a heuristic idea in the sense that there is no formal proof why it works, and in some applications it can actually hurt the performance. Here, however, it was very helpful. The dropout sets the output of each hidden neuron to 0 with some probability. Here, this probability was set to 0.5. And we do this only at training time. The neurons during training are dropped out. We will use these neurons at test time and validation time. The neurons which are dropped out in this way do not contribute to the forward pass and do not participate in the backpropagation. Effectively, every time an input is presented, the neural network samples a different architecture, but all of these architectures share the weights of the neurons that were not dropped out. It's like saying we don't want super strong neurons who would overfit to the training data. Even if we delete some neurons, the networks should still perform well. The AlexNet network has so many parameters that without this dropout trick, the network would actually exhibit substantial overfitting. As a side effect, this dropout trick roughly doubles the number of iterations required by the training method to converge. Here we used 0.5 probability for the neurons to be dropped out. This, however, is a hyperparameter and needs to be tuned in each application. As we discussed, on the first convolutional layer, there are 48 convolutional kernels learned by GPU1 and 48 other kernels learned by GPU2. The size of these kernels are 11 times 11 times 3. Here I'm visualizing these kernels as RGB images. The top 48 kernels were learned on GPU1 and the bottom 48 kernels were learned on GPU2. It's interesting to observe that these filters look like Gabor wavelets. They are also similar to filters of another unsupervised machine learning method called independent component analysis, or ICA. When we train ICA on images taken from nature, usually this ICA algorithm learns very similar features to these. It's also interesting that these filters are similar to the receptive fields of some cells in our visual cortex. The results of AlexNet on the test data set can be seen below. The top 1 error rate is 37.5% and the top 5 error rate is 17%. On the ImageNet Challenge competition in 2012, this AlexNet achieved 15.3% top 5 error rate, but the second best team achieved only 26.2% error rate. So AlexNet won this competition by a very large margin. This was the moment when many other researchers started to use deep convolutional neural networks and GPUs for training image classifiers. Here I'm showing some results on the ImageNet dataset. On the top row, you can see the original images, below them the class labels, and 5 top guesses of the algorithm. These bars indicate how confident the algorithm was in its prediction. As you can see, it was able to predict the labels of all of these images. In the bottom row, I'm showing 4 examples where the algorithm made some mistakes. These mistakes, however, are often quite reasonable. For example, on this very first image, the human labelers labeled this image as grill, while the neural network labeled this as convertible, which is also a reasonable estimate. Similarly, on the third image, the label is cherry, but the algorithm labeled this as Dalmatian, which again makes sense. On the last image, the correct label is Madagascar cat, but the algorithm labeled this as squirrel monkey. But to be honest, I don't think I could have labeled this image correctly either. As we discussed, the last layer of AlexNet is 1000 dimensional, since we have 1000 image categories. The layer before this output layer is 4096 dimensional. Interestingly, this feature vector can be used in many applications as a feature representation of the original image. Here we show an application to reverse image search. In the left column, we show 5 query images. We calculate their 4096 dimensional feature representations, and we show 6 images from the training set whose feature vectors are the closest in Euclidean distance to the feature vectors of the query images. As you can see, these images are indeed very similar to each other. If we simply calculated the Euclidean distances in the original image space, that wouldn't work. Euclidean distances in the original image space can't even handle object translations well. If we have an image with an elephant on the left and another image with an elephant on the right, the Euclidean distance of these two images can be very big. However, the 4096 dimensional feature vector representations of the two images will be very close to each other. As we have seen, AlexNet works great, but there are many improved neural networks which can classify images even better. A famous example is the VGG neural network. VGG stands for Visual Geometry Group, which is a research group at University of Oxford. This network was published at the Very Deep Convolutional Neural Networks for Large-Scale Image Recognition paper by Karen Simonian and Andrew Zisserman at iClear 2015. This network uses very small 3x3 convolutional filters and goes deeper, typically using 16 or 19 convolutional and fully connected layers. The max pooling layers don't have any trainable parameters, and they don't use ReLU activation functions either. VGG shows a significant improvement on the prior state of the art. In the ImageNet challenge in 2014, it got the first and second places in the localization and classification tracks, respectively. We will discuss its details now. VGG 16 uses convolutional layers, max pooling layers, ReLU activation functions, and on the last layer it uses softmax activation function. VGG 16 consists of blocks, and each block consists of a sequence of convolutional layers, those are colored blue, which are followed by a max pooling layer, which are colored red. The same kernel size, 3x3, was applied over all convolutional layers. The authors used a padding size of 1 to keep the size of the output after each convolution layer the same. A max pooling of size 2x2 with size of 2 was also applied to halve the resolution after each block. This max pooling doesn't have any trainable parameters. For each subtensor of size 2x2, it just calculates the max of that subtensor. VGG16 is composed of 13 convolutional layers, 5 max pooling layers, and 3 fully connected layers. Therefore, the number of layers having tunable parameters is 16 because it has 13 convolution layers and 3 fully connected layers, and the max pooling layers don't have trainable parameters. That's the reason why this model is called VGG16. The number of filters in the first block is 64. Then this number is doubled in later blocks to 128 and then 256 until it reaches 512. This model is finished by 2 fully connected hidden layers and 1 output layer. The 2 fully connected layers have the same neuron numbers, which are 4096. The output layer consists of 1000 neurons corresponding to the number of categories on the ImageNet dataset, and this very last output layer uses softmax activation function. It's very easy to create convolutional neural networks in deep learning frameworks such as PyTorch, TensorFlow, Keras, or others. Here I'm showing a few examples about how to create, train, and evaluate convolutional neural networks in Keras. First, We will see a simple convolutional neural network example on the MNIST digit dataset, and then we will discuss how to create a VGG neural network using Keras. Below, I'm showing two Colab notebooks that use Keras to create, train, and evaluate convolutional neural networks on the MNIST dataset. The first one is a very simple basic code. The second one contains a bit more details. Let's take a quick look at the first Jupyter notebook. With this NVIDIA SMI code, we can check the status of the GPUs. As you can see, we got a Tesla T4 GPU, and currently there's nothing running on it. We import NumPy, TensorFlow, and Matplotlib. In the MNIST dataset, we have 10 classes, the 10 digits from 0 to 9, and the shape of the input images are 28 times 28 times 1, because these are grayscale images. We load the dataset with this command. It creates a set of training images with their corresponding Y-train labels, and a test set where X test contains the test images and Y test contains their labels. We convert the images to be floats and then normalize them to be between 0 and 1 instead of 0 and 255. And we also convert the labels from integers to one-hot codes. So now the test set size is 10,000. We have 10,000 test images, and each test label is a 10-dimensional vector. Let's look at, for example, the very first one, how it looks like. By test 0. As you can see, it's a one-hot encoded label. Now we build our model. The first layer is an input layer. This is where we load the images. Then we add a 2D convolution with 32 channels. Kernel size is 3 times 3, and we apply a ReLU activation function on this layer. Then we add a max pooling with size 2 by 2. So in each 2 by 2 matrix, we will just calculate its maximum. Then we add another convolutional layer with kernel size 3 times 3, and this will have 64 channels. Then another pooling layer. We flatten everything out, just create one giant vector. Then we add a dropout layer. And finally, we add a dense layer that maps everything to 10 dimensions. And we apply a softmax activation function because we want to output class probabilities. So this is very simple. And with the model.summary command, we plot how our neural network looks like. Here you can see the list of the layers, their shapes, and in this column we even list how many trainable parameters we have in each layer. Altogether, this neural net has a bit more than 34,000 trainable parameters. There's also this plot model command, which can also visualize the structure of the convolutional neural network. And let's even show the shapes of the layers. Here you can see the input layer. It gets 28 times 28 times 1 dimensional images. This none just means that we don't specify beforehand the batch size that we use for training. It could be any number that we will later specify. Then the input goes into a convolutional layer. This convolutional layer gets 28 times 28 times 1 dimensional images, and because the size of the convolution is 3, it creates 26 times 26 dimensional images, and we also created 32 channels. After that, it goes to a max pooling where in every 2 times 2 submatrices we calculate their maximum. So it will halve the dimensions of the images. So the new dimension will be 13 times 13 times 32. Then it will go into another convolutional layer, then another max pooling layer. That max pooling layer from the 11 times 11 times 64 dimensional tensors will create a 5 times 5 times 64 dimensional tensors. We flatten everything out. That will create a 1600 dimensional vector, and then we added another dropout layer, and finally we map the 1600 dimensional vectors into a 10-dimensional output vector where we use softmax activation on the top of this. As I said, we didn't specify the batch size before, now we do it. We say the batch size should be 128. We will use 15 epochs to train this neural network. With this model that we compile the model, we will specify the loss function, which in this case is a cross-entropy loss. We specify the optimization algorithm that we use, in this case is an Adam optimization method, and we can also specify the metric that we care about. In this case, it will be classification accuracy. And then with the model.fit command, we can just train the neural network. It needs the training set, the training labels, the batch size, how many epochs we are going to use for training, and if we want to use validation, we can specify that here too. It's a small data set and a small neural network, so the training will be quite quick. The training is done. Now we are ready to evaluate the model, and we can use the model.evaluate command for that. It just needs the test set with the test labels. And as you can see, the test accuracy is 99%, which is pretty good. And let's see how it works in a practice. Let's choose test image. We use the 26 image in the test set. Let's visualize that test image. It looks like this. And then we can use this test image to predict its label with the model.predict command. And as you can see, the predicted label is 7. And indeed, this image looks like a 7. This other MNIST code is very similar to the previous one. It just contains a bit more details. Let's quickly review it. We import NumPy and pandas. Then we import Keras. From Keras, we import the dense dropout activation and flatten layers. We also import the 2D convolution and the max pooling layers. We will visualize our model with the plot model command. We will use the image command to display images. We import some other utilities. Finally, from Keras, the datasets, we can import the MNIST dataset. We load the dataset and create the training set and test set. As you can see, in the training set, we have 60,000 images, each with size 28 times 28. With the matplotlib imshow command, we can visualize these training images. Here's the first one that looks like digit 5. As you can see, we have 60,000 training instances and 10,000 test instances. These are all grayscale images, so they only have one color channel. We specify that here and reshape the datasets accordingly. And as you can see now, the training set has 60,000 images, and each training instance is 1 times 28 times 28 dimensional. We convert them to floats, and then we normalize them to be in the range of 0 and 1. Now, because the training labels are integers, we need to convert them into 1-hot encoded vectors. We can use that with this NumPy utility, which can convert integers into one-hot encoded vectors. And as you can see here now, the training labels are one-hot encoded vectors indeed. Now we are ready to create our model. We will add layers one by one. First, we add a convolutional layer that has 32 channels and the kernel size is 3 times 3. We will use ReLU activation on this layer, and it gets the input images as inputs. They have size 1 times 28 times 28 as we discussed before. Now we have a model that has one convolutional layer, and we can check what's the size of the output after this layer. We created 32 channels, and because the convolutional kernel is 3 by 3, it creates 26 times 26 dimensional images. If we want, we can add another convolutional layer that creates 32 channels, and if the kernel size is 3 times 3, then the size of the output will be 32 times 24 times 24. We can add the max pooling then if we want, and if the size of the max pooling is 2 times 2, then it will halve the size of the images in the previous layer, so the new size will be 12 by 12, and we still have 32 channels. If we want, we can add a dropout layer with some probabilities of dropping out neurons that will not change the size of the layers. We can flatten everything out. The size in the previous layer was 32 times 12 times 12. If we flatten this out, then the size will be 4608 dimensional. And then we can add a dense layer after that maps this 4608 dimensional vector into a 128 dimensional vector. We can add another dropout layer if we want. And finally, we can map everything into a 10-dimensional vector because we want a 10-dimensional output because we have 10 different categories, and the activation will be softmax activation function on this output layer because we want to output probabilities. So we can visualize the neural network we just created with the model.summary command. As you can see, this neural network has 600,810 trainable parameters. We can also use the plot model command to visualize it a bit differently, where you can see the input and output shape for each layer and the name of the layers. When we are done, we can compile the model, which means we specify the loss function and the optimizer and the metrics we care about. Our loss function is cross-entropy loss, the optimizer is Adam optimizer, and we care about the accuracy. And we are ready to fit the model. We just have to give the training images and training labels. We can specify the batch size and how many epochs we want to use for training. And after a few minutes, the training will be done. With the model.evaluate command, we can evaluate the accuracy of our model. We just have to provide the test set and the test labels as input. And as you can see, the accuracy is 99%. So this is a pretty good model for classifying images in the MNIST dataset. To check the predicted labels on any test images, we can just use the model.predict command, and for each test images it predicted the output labels. The predicted output labels are 10-dimensional vectors. Let's look at one of them. For example, the very first one. So as you can see, the predicted outputs are 10-dimensional vectors where the coordinates of these vectors are non-negative and they sum to 1. So these are probabilities. And if we really want to predict what is that integer, then we just calculate where this vector has maximum value. Then we are done. We can even use this crosstab function from the pandas toolkit, and then we can create this confusion matrix where we use the test labels and the predicted labels, and then it can calculate this confusion matrix. As you can see, it's very diagonal, which means that we were almost perfect on predicting the class labels. If you want to list all the layers, you can just use that with the model.layers command. And here you can see that we had a convolutional layer, then another convolutional layer, then a max pooling layer, and so on. To get the weights of the layers, you can select a layer. For example, model.layers 5 selects the 5th layer, and then with the .getWeights command, you can get the weights of that layer, and with the .shape command, you can get the shape of those weight tensors. So here you can see the shape of the trainable weights on different layers. We can also visualize some of the misclassified images. I'm doing that and put them into this test wrong list. So those are those images in the test set where the predicted label is different from the test label. Let's look at the 5th element of this list. Here you can see that the predicted label was 9, but the true label was 8. And we can even plot some of these misclassified images to see how they look like. And this code will just do that for us. Here we plot 100 misclassified images from the test data set. And the red numbers are the predicted labels, the blue numbers are the true labels. For example, here the true label was 8, but we predicted 2. Here the true label was 5, we predicted 3. Here the true label was 2 and we predicted 7, but it indeed looks more like a 7. And so on. Here the true label was 5, we predicted 6, and indeed it almost looks like a 6. As we discussed before, the keras plot model command can be used to visualize the convolutional neural networks. It shows the network structure with a graph where the nodes in the graph are these blocks, and these blocks are connected with each other. These blocks contain the name and type of the layer. For example, this one is an input layer, this was a convolutional layer, this was a max pooling layer, this is a dropout layer, this one is a fully connected layer, this one is a flattened layer, and so on. It also contains the size of the input that the layer requires and shows the size of the output that the layer produces. Where we see a none in the description, it just means that this parameter is not specified when we created the network. For example, it can be the size of each mini batch we use for training, and we specify that size later. These arrows indicate how the layers are connected to each other. Here from this layer we are going into this one. Another useful comment to visualize the structure of the neural network is the model.summary command. It also shows the name and shape of the layers. The connected to column indicates which layer gives input to this layer, and the param column shows the number of trainable parameters in that layer. As we discussed, the model.layers.getWeights.shape command can be used to get the shape of the weight parameters in any given layers, and we can use it to calculate the number of trainable parameters. For example, we can see that on the very first convolutional layer, we have 32 channels, and each channel has a convolutional kernel size 133. We also have an additional bias parameter on this layer. So the number of parameters on this layer is 32 times 3 times 3 times 1 plus 1. So it's 32 times 10, which is 320. Similarly, the next layer also has 32 channels. Each channel has a convolutional kernel with size 32 times 3 times 3. Again, we have an additional bias parameter on this layer as well. So the number of trainable parameters on this layer is 32 times 3 times 3 plus 1, which is 9248. The first dense fully connected layer gets a 4608 dimensional input and produces a 128 dimensional output. It also has a bias parameter as well. So the number of trainable parameters on this layer is this quantity here, which is almost 590,000. This way we can calculate the number of trainable parameters for the whole neural network, and if you add all these numbers for each layer, we get that we have a bit more than 600,000 trainable parameters. As we discussed, if X test denotes our test set, then we can use the model.predictClasses command to predict the class labels on the test set, and then we can use the crosstab function from the pandas toolkit to create a confusion matrix. And as we can see, this confusion matrix is almost completely diagonal, which means that the neural network works very well on these test images. It's very easy to create the whole VGG16 neural network in Keras. I'm showing its Keras code on this slide. As you can see, at each step, we can just add a 2D convolution, a max pooling, or a fully connected dense layer with the model.add command. And we just need to specify the shape, the padding, the stride parameters of these layers, as well as their activation functions. In this case, we just used ReLU or softmax activation functions. When the model structure is done, we compile the model by specifying the loss function. In this case, we use cross-entropy loss function. We specify the optimizer. In this case, it's SGD with learning rate 0.01. And we can also specify the metric we care about, which in this case is accuracy. Here, I'm showing all the layers and the number of trainable parameters of the VGG16 network. As you can see, it has more than 138 million trainable parameters. A big brother of VGG16 is VGG19. Here, instead of 16 layers with trainable parameters, it has 19 layers with trainable parameters. It has a few more convolutional layers, but other than this, it's very similar to VGG16. It's very easy to create the VGG19 neural network in Keras. I'm showing its Keras code on this slide. As you can see, at each step, we can just add a 2D convolution, a max pooling, a zero padding, a dropout, or a fully connected dense layer with the model.add command. And then we just need to specify the shape, the stride parameters of these layers, as well as their activation functions. If we already have a trained model, then we can use the model.loadWeights command to load the weights back to the model. With the model.summary command, we can visualize the VGG19 network and show the shape of the layers and the number of trainable parameters on each layer. The green text shows the names of the layers. With red color, I'm showing how to verify that the number of trainable parameter calculations are correct. For example, on conv2.1 layer, it gets input from a convolutional kernel with 64 channels, and we know that the kernel size is 3 times 3. So this convolutional kernel has a size 64 times 3 times 3. It also has one extra bias parameter. So we have 64 times 3 times 3 plus 1 parameters for each channel. And this layer creates 128 channels. So the total number of parameters is 64 times 3 times 3 plus 1 times 128, which is almost 74,000. And so on. We can calculate all of these for all the other layers. If we add all these trainable parameters, we get that VGG has almost 144 million number of trainable parameters. On the very last layer, we use softmax activation function, which is defined by this expression, where here wj are the parameters and x is the input to this layer. We have 1000 classes, so this creates a 1000-dimensional vector, and the elements of these vectors are non-negative and they sum to 1, so we can think of these elements as probability distributions. Finally, we can show the whole VGG19 structure with this Keras plot model command. As you can see, it gets an image with size 224 times 224, and this image has RGB channel. Then it goes to zero padding and convolutional layers, and at some point to max pooling layers, and so on. It goes through several layers. Some of the convolutional layers increase the number of channels. For example, here from 256 we increase the number of channels to 512. We can also see that the max pooling layers aggregate the information and halve the size of the images. Here the size is 56 times 56, but after the max pooling it becomes 28 times 28. And finally, the last max pooling creates a layer that has 512 channels, and the size of that aggregated image is only 7 times 7. We flatten this out and we got a 25,088 dimensional vector. With a fully connected layer, we reduce this to 4096. We reduce this further to a 1000-dimensional output layer, and on this very last layer we use softmax activation function. The top one error of VGG19 on the image data set was 25.5%, and the top 5 error was 8%. The network is more complicated than AlexNet, but these results are also significantly better than the results of AlexNet. I want to mention that the current state of the art for the top 5 error is only a few percent, and it is about the same level, maybe slightly even better, than the human labeling accuracy. On this image, these are the top predictions of VGG19. As you can see that the top ones are indeed not too bad. As you can see on this image, although the prediction of VGG19 is not perfect, it's not that bad either. I'm wondering if, because it can see these wires here, it infers that this bus might be a trolley or a tram. Other than classifying images of the ImageNet dataset, you can also use convolutional neural networks to classify other image datasets. Here, I'm showing you an example where we can try to classify sport events. On certain frames, we ask the network to predict the sport event of that frame. These results are quite impressive in my opinion. Here you can see the top predictions of this neural network. I already mentioned PyTorch, TensorFlow, and Keras deep learning frameworks, but you should know that there are many other ones. Here is a list of a few of them. Thanks for your attention for now. Next time, we will continue with some other applications.